Hey guys, thanks to Tyler for starting off the lesson. Now I'm going to introduce a new concept called the moment of mass. So you can title this Moments of Mass. Sorry. Now, Wikipedia defines a moment in general as the product of a distance and a physical quantity. So in this case, the moment of mass would be the product of distance and mass, where distance is the distance to the center of mass. Now, there are three different moments of mass you should be familiar with. First, the zeroth moment of mass. This is just the total mass of something, and certainly in this lesson, it will just be a lambda, so total mass, and it's represented by 1 times m. You might be thinking, well, that's not a product of a distance and mass, it's just the mass. And, that kind of makes sense because it's the zeroth moment, so it's implying that the distance doesn't really matter right now, and you'll see why right now. The first moment. This is the tendency to rotate about an axis. And that is represented by d times m, where d is the distance to the center of mass. Now there's one more called the second moment. If you've taken physics, you should all be familiar with it, and it's just called the moment of inertia, which is kind of the resistance to angular motion. So moment of inertia. And in general, the general form for a moment of inertia is d squared times m, where again, d is the distance to the center of mass. So it's good that you should be able to differentiate between these. And in this part of the lesson, I'm going to focus on the first moment. So you can title this First Moments of Mass. Now, I'm going to draw a graph and I'm going to leave it up for the next couple parts. And it's just going to be a simple 3D graph, try to copy mine, y, x, z, of a rectangle. And this will just represent a lamina. Now, remember that the first moment of mass was the tendency to rotate about an axis. In this case, about the x-axis and the y-axis. Now, if you could guess, m sub x is the moment of mass with respect to x, and that is the tendency to rotate about the x-axis. And there's another one called my, which is the tendency, tendency to rotate about the y-axis. Now, the formula for these look very similar to the formula that Tyler mentioned the last lesson, just for mass. So I'm going to leave a part blank, but if you look at this, everything else about this is exactly the same as the mass formula that Tyler introduced last lesson. You have the double integral over the region R, you have the rho function, which represents density, and you have the area function, or the area, dA, which could be dx dy or dy dx, depending on which one is easier or which one you choose to do. Now, remember that the moment of mass with respect to x is the tendency to rotate about the x-axis. So you have your mass density function right here. Now, the tendency to rotate about the x-axis, if you think about it, if most of the mass is concentrated here, it will be a lot harder for this lamina, or this region, to rotate about the x-axis than if the mass was concentrated right here. Now, if you think about it, what are these little slivers? Well, they're y values. They're y values. And so the tendency to rotate about the x-axis would be measured in y values, because as you get further along, it gets easier and easier to rotate the more the mass is concentrated. So you can also think about this as concentration of mass along the y-axis. And the same exact thing goes for the moment of mass with respect to the y-axis. It's the double integral of x density function times the density function dA, where this is the concentration of mass along the x-axis. Because if you think about it, if all of the mass was concentrated here, it would be a lot harder for this thing to rotate around the y-axis than if it was all concentrated right here. Because if you just think about it, let's say you have this pen and a 1 pound block or whatever is right on the tip. It would be really hard to keep this thing up. But if the 1 pound thing was right here, it would be a lot easier. So the same amount of force here would do more work than, or would be more powerful than right here. So that's the general understanding of why the moments of mass kind of look counterintuitive. It's because the concentration of mass along, or that would make it easier to rotate about the x-axis, would be measured in little slivers of y values. Okay, so I hope you understand the general reasoning behind why that is. And now I'm going to introduce a relatively similar concept. You've all been familiar with it, and you may just not have explored it mathematically, and it's called the center of mass. Now, I should have kept this graph up, but it's all right. Draw it again. So the center of mass, if you think about it, let's say this is a lamina with uniform density. It would be the point in the very center, because if you were to have that point right over your finger, you would be able to balance the paper. So my finger is pretty much under the center of mass of these papers. So remember, it's a coordinate pair because it's a point. The center of mass is a point. And so the x-coordinate would be called x bar. This is called x bar. And if you think about it, it is the average mass of all of the x, because this is an x-coordinate. The center of mass for the x-coordinate will be somewhere along there. Now, why does this feel familiar? Well, wherever this is, it will be the equal concentration of mass below it and above it. And so, remember that the moment of mass with respect to y was the tendency to move about the y-axis. So it was kind of the density function for this whole thing, the concentration along this whole entire thing. And x bar is just the average. And so since the moment of mass with respect to y is measured in x values, and it's the concentration of mass along all of the x's, the x-coordinate would just be the average of them, because it's the place where the mass is equal above it and below it. So this would be measured as the moment of mass with respect to the y-axis over the total mass. And the same thing goes for the y-coordinate. It's called y bar, and that's the moment of mass with respect to the x-axis over the total mass. Now the center of mass is x bar, y bar. And I really want to emphasize the point that x bar is pretty much measured by the concentration of, or how easy it is to move this lamina over the y-axis, and it's vice versa for the y-coordinate. And I really hope that makes sense, because I think it is very important to understand in this lesson. Now that we kind of have a conceptual understanding, I'm going to move to an example, and I think this would be example 3. So it might be a long example, so example 3. Find mass and center of mass of the lamina bounded by y equals the square root of a squared, which is just a constant, minus x squared, and y equals 0, where the density is constant, equal to constant k. Now, you might want to pause it and try it for yourself, using the formulas I just gave you, and unpause it when you want to see the answer. Okay, so the first objective we want to do is find the mass, because that is the first thing we need for both the mass and the center of mass. So first is finding the mass. Remember that the formula is the double integral over region R of, what is it, the density function with respect to the area. Now, first, before we actually do this, I think it would be really good to graph it. And so I'm going to just do a simple graph. And if you look at this function and you want to try to simplify it, you get y squared equals a squared minus x squared, and y squared plus x squared equals a squared. So this is just a circle with radius a, but it's also bounded by y equals 0. So it would be a half circle bounded by the y-axis. So it would look like this, where the radius is a. So this would be negative a, 0. This would be a, 0. And that would be 0a. Okay, yeah. So that distance is a. And, oh yeah, this is y equals 0, and that's y equals a squared minus x squared. Okay. So the first thing is to find the mass. Now, what we want to do is probably just integrate over this way, because then we could just we already have the y function, and we could just take little slivers from negative a to a. So what that would look like is the x values would go from negative a to a. The y values would go from 0 to the square root of a squared minus x squared. And the integrand would just be k, because remember the density function is just k, and that would be x, y, so dy dx. Yes, and I will integrate this pretty quickly because it's a pretty simple integral. So it would first integrate the center, which would look like this. Y from 0 to the square root of a squared minus x squared, and with respect to x, which is the integral from negative a to a times k of the square root a squared minus x squared dx. Now this looks pretty terrible, right? Pretty bad. The thing is, that was the function here, which ended up just being a semicircle. And remember from last year in Calc BC the integral from the left bound to the right bound of a function was just the area beneath the curve. So the area beneath this would just be the area of a half circle with radius a. So this is just equal to k times the area, which would be pi a squared over 2. So the mass is just k pi a squared over 2. And that is step 1 of the problem. Next, we have to find the center of mass. If you look at it, P, the density is just a constant, so it's uniform density around this whole thing. When it is uniform density, or even sometimes when it's not, I want you to always look for symmetry. If you look for symmetry, sometimes you will find shortcuts. In this case, there's a very good shortcut. The center of mass is just where mass is equally concentrated on both sides of the axis. And in terms of the y-axis, or the x-coordinate, it's just x equals 0. And so that would mean that x bar equals 0. Remember that x bar was just my over the mass. So now we just have to find mx. We don't even need to find my because we already know what x bar is. The next step we need to find is mx because we don't need to find my. So we find mx, which is, remember the formula, double integral of y times the density function times with respect to the area. We'll do the same exact thing as finding the mass, just adding this little y here. So it would be from negative a to a, from 0 to a squared minus x squared of ky dA, or ky dy dx, because we're taking little dx's and finding dy's along the whole thing. So integrate the inside, so you get 1/2 ky squared, because the middle is with respect to y, and that's just from 0 to the square root a squared minus x squared and with respect to x. This is just equal to 1/2 k integral from negative a to a of a squared minus x squared. And I took a little shortcut, but in the middle it's y squared from 0 to square root of a squared minus x squared. And so you'd end up with just squaring this right here. And that's why you'd get that. Now to integrate this, I'm going to take a few shortcuts here and say that that is equal to 1/2 k times a squared minus 1/3 a cubed minus a squared minus negative a cubed. Now, I don't have enough space, so I'm going to erase this. Now that is just equal to 2/3 ka cubed. So now that we know that, and we also know the mass, and we also know x bar, we're able to find y bar. So remember that y bar was just mx over m, which is equal to 2/3 ka cubed all over 1/2 pi ka squared, because that's what that was what the mass is that we found. This simplifies to 4a over 3 pi. And so now that we have y bar and x bar, we know that the center of mass, which is equal to the average mass of along the x-axis with the average mass along the y-axis, or x bar, y bar, is equal to 0, 4a over 3 pi. And there is your center of mass.